All right, so first major topic in thermochemistry was that calorimetry, studying heat transfers using that equation mass times specific heat times temperature change. Here's the second big topic in thermal. It's something called Hess's law. I think you're going to like this. Hess's law refers to reactions that can take place in more than one step. Kind of reminds me of that kinetics that we were doing, where there were those elementary steps and we wanted to make sure that they added up to the overall balanced equation. This looks very similar, but now we're going to look at it from a thermal or energy transfer perspective. So it says Hess's law, in going from a given set of reactants to a given set of products, the change in enthalpy, or energy change, is the same whether the reaction takes place in one step or a series of steps. And again, that kind of relates back to the kinetics, where there were multiple mechanisms that could be acceptable, and it was really hard then to say which one was exactly right. That's really the best we could do, is to say, they gave us the balanced equation, the rate law in the lab matches the rate law of the proposed mechanism. So now we'll look at the energy side of these things. So for example, we could have this one-step reaction where nitrogen reacts with oxygen, producing nitrogen dioxide, or this could happen in two steps. And again, some similar things from kinetics. You can always cancel like terms. So we have, in the first step, nitrogen and oxygen producing nitrogen monoxide. And then in the second step, that nitrogen monoxide is consumed as we react it with more oxygen to finally form the nitrogen dioxide. You could cancel these guys. Remember, when something is produced and then consumed, it was called an intermediate. That nitrogen monoxide is not really part of the final balanced equation. It's formed in the first step, used up in the second. Whether I do this as one step or two, the total energy change is the same. In the one step, it was 68 kilojoules, and in the two step, we just add the energy change from each individual step to get the overall energy change. Well, that makes sense, right? Okay, so here are some other little things that will pop up when we look at Hess's law. When we're looking at the intermediate steps, we want to try to figure out a way of manipulating the intermediate steps so that we get the overall desired reaction. If we need to reverse one of the reactions, one of the intermediate steps, then we're going to reverse the sign of the delta H. This will make much more sense in like 2 seconds. So there are times when we might need to reverse a reaction. Some things on the product side, we want it on the reactant side. So we can switch the products and reactants, but then we're going to switch the sign of the delta H as well. The other option, the magnitude of delta H, is proportional to the quantities of reactants and products in the reaction. If by chance the coefficients need to be multiplied, so maybe I have an intermediate step like this first one. Xenon plus 2 fluorine forming xenon tetrafluoride. Excellent. What if for some reason I needed to double that? In the desired reaction, I needed to form 2 xenon tetrafluoride. Then the value of the delta H is also multiplied by the same number. So if we doubled the coefficients in the balanced equation, check it out. We just double the delta H. Then the second one, that reaction in the middle, kind of shows that first option. If you needed to flip a reaction, so if we wanted to flip the reactants and the products, maybe I wanted the xenon tetrafluoride on the reactant side, then notice we just flip the sign of the delta H. Forming xenon tetrafluoride is an exothermic reaction. So if I want to decompose the xenon tetrafluoride, I need to add 251 kilojoules. That makes sense, right? Okay, so I really think that Hess's law is kind of fun. I think these problems are kind of fun to solve. Here is this proposed reaction. Carbon reacting with water, forming methane and carbon dioxide. We want to calculate the delta H. They have given us 3 steps. So we want to try to manipulate these three intermediate steps so that I get the overall balanced equation. And whatever I need to do to the intermediate step, that's kind of the same thing that I do to the delta H. In the end, we'll just add them all up. Okay, so I usually just attack these from whatever comes first in the equation. So I need 2 carbon on the reactant side. So I look at my options, I look at my intermediate steps. Step 1 looks promising. Here's carbon on the reactant side, but I need 2 carbon on the reactant side. So I'm going to take this first step and I'm going to multiply everything times 2. So we'll then have 2 carbon plus 2 waters. We're going to form 2 carbon monoxide and 2 hydrogen. And then if I do my little delta H, and these are in units of kilojoules. I'm assuming now that I just noticed this, that's probably supposed to be a kJ. Whoopsie. Not there. kJ. I'm assuming that's got to be kilojoules, right? So let's put these in units of kilojoules. There we go. So all I'm going to do then is multiply 131.3 times 2. And we're going to say that's 262.6 kilojoules. Positive. And again, if you don't put the positive in, it's assumed that you mean endothermic. Okay, so I got the 2 carbons. Excellent. Actually, this works out kind of nice because I have 2 waters on the reactant side, and that is what I want. But now let's say I check the product side. I want 2 methane. Oh, and I forgot to put a little 2 in there. That's 2 hydrogen diatomic. So now I look for methane, CH4. I have methane in that 3rd elementary step, but it's on the reactant side, and I want it on the product side. So let's try taking this 3rd step, and let's flip it. So we'll reverse the whole thing. So we would have the 3 hydrogen and the carbon monoxide, and we'd form the CH4 plus water. And then I flip the sign of the delta H, so this will become negative 206.1 kilojoules. All right, I like this. It's kind of fun, right? So let's just kind of do inventory here. We have a few things that we want. We want these 2 carbon. I want these 2 water. I want the CH4 methane. I've got a couple junky things hanging out here. Let's try to get some carbon dioxide on the product side. And I promise, these things will always work out. Like the elementary steps given will always be able to manipulate into the overall balanced equation. I promise there's no tricks. So let's see if we can get that carbon dioxide. I haven't used that middle step yet, and it does produce carbon dioxide. It's the only option for carbon dioxide. So let's just use this guy straight up. Plus the water, forming the carbon dioxide. I want you. And some hydrogen. And then we'll just leave this as negative 41.2 kilojoules. Okay, so I want this. I have the reactants and products, but does everything else cancel? There's, again, a bunch of intermediates and some junk in here that I don't want. So let's see what we got. I have 2 carbon monoxide produced in the first step. Ah, yes. But I can get rid of 2 from the other steps. We consume them both. I like that. I have a total of 1, 2, 3 hydrogens on the product side, and I do not want those anywhere in my balanced equation. Good thing they cancel with these 3 hydrogen. Out! They're gone. And then here's that extra water. I wanted 2 on the reactant side. I form 1 in the second step. but then I consume it in the third. Gone. So check it out. We have the desired balanced equation. We got the 2 carbons, the 2 waters. We produce the methane and the carbon dioxide. So if this adds up to the desired equation, which it does, whoopsie, 2 carbons. Why was I writing carbon monoxide? 2 carbons, 2 waters, the CH4 methane, and the carbon dioxide, then all I got to do is add those delta H values, and we have the overall energy change for this reaction. So if we add these up, let's say we have, oh, interesting, 15.3 kilojoules for my overall delta H. And again, what happens, you might have some steps that are endothermic, some steps that are exothermic. This overall equation ends up being slightly endothermic. Pretty darn cool, huh? There it is, Hess's law. Kind of fun. Let's try one more while we're at it. All right, let's attack this ammonia problem. Ammonia, 3 oxygen, forming some nitrogen and water. Yikes, 6 waters. Okay. So again, I usually just start with whatever comes first in the balanced equation. So if I want 4 ammonia, I just look at my elementary steps. I see what I have available. Let's try to get 2 ammonia. So how about we take this second step and we multiply her by 2. So we'll have 4 ammonia. I want U plus 6 dinitrogen monoxide. I do not want that. So I'm hoping that at some point we can cancel it. Then I'm going to get, yikes, 8 nitrogen. I don't know if I want 8 of those. And 3 waters. Times 2 is 6. Ooh, I like that. So we multiply all those coefficients by 2, and then we'll do the same thing with the delta H. This is delta H in units of kilojoules. So we'll take that negative 1012 and multiply by 2 for negative 2024 kilojoules. Okay, so I wanted the ammonia. I like that, 4 ammonia. And I do want these 6 waters. That worked out kind of slick, huh? I'm hoping to get rid of that dinitrogen monoxide and maybe a little bit of nitrogen. And again, I promise these always work out. So for example, let's just move down the line. In the original balanced equation, I want 3 oxygen on the reactant side, and I don't have that yet. So I'm probably looking at that first elementary step, which produces oxygen. If I want it on the reactant side, we'll just flip it. And then I would only have 1 oxygen. I would like 3. So watch this. Let's get really nuts. We'll take this first reaction. We'll not only flip it, but we'll also multiply it by 3. Whoa, that's crazy. Yeah, you can do that all at once. Okay, so let's flip it and multiply by 3. So we'll have the 3 oxygen that I want. Then we're going to have 6 nitrogen. Interesting. And then I flip it for, excellent, 3 times 2. I did not want this thing. 6 of these boogers. So then I'm going to take that negative 164 kilojoules. We're going to make it positive and multiply by 3. So that will give me 492 kilojoules. Okay, does this work? I hope it does. I wanted these oxygen, so that's good. Yes, this is going to be all right. I do not want these little guys. That's gone. Do you remember the term, if we add something and then we get it back later? You're saying catalyst, right? Wow, isn't this awesome that we get to the end of the course and we're like almost kind of reviewing for the AP test and we're not even trying to? Yeah, that would be a catalyst, something that's added but then you get it back in a later step. And this is great too. So I do want some nitrogen on the product side, but I only want 2 nitrogen. Well, check it out. Here I produce 8, but then I consume 6 of them. So we could cancel these 6, and then let's drop this guy down to 2. And that's exactly what I want. So I got the 4 ammonia, I got the 3 oxygen. Now I have the 2 nitrogen. I was able to simplify that. And yes, the 6 water, this is perfect. I get the overall balanced equation, the 4 ammonia, and the 3 oxygen, and I promise they will always work out. O2, the 2 nitrogen, the 6 waters, and then we're just going to add those 2 elementary steps, and we will say the overall reaction releases 1,532 kilojoules. Exothermic overall. First step, very exothermic. Second step, slightly endo. But if we add the 2, we get the overall change for the balanced equation. Piece of cake. So again, if you think that this is awesome, try a few in the homework. If you're getting them right, you're in a good place. If you feel like you need more practice, we'll throw a couple more in the next video.